I called this more C of M. What do you think C of M stands for? What? Conservation momentum. I just didn't feel like writing it out. Okay? So we've been talking about crumple zones and how the key to minimizing injury in a car accident is to increase the time of collision. Since that will, what does increasing time lower? Lowers force, right? How does this work in a smart car? Well, the engineers cleverly decided that the engine would be the crumple zone. Put your pencils down, look up. So we'll start at 5 minutes, which is right about there. So we have a remote control smart car, and we're going to crash it into a concrete barrier at 70 miles an hour, about 120 kilometers per hour.
Kim's James, 10 seconds. 10, 20, 30, 5, keep it straight, make it. 40, 5.
From 70 miles an hour to naught in 1 second. The little smart hit with such energy that it moved 20 tons of concrete, leapt into the air and rebounded to the side of the road. We didn't know what we'd find when we reached the wreckage.
I mean, that was a pretty intense collision.
The steel cage has certainly done its job really well. You can still see the original shape, just that one nasty kink there. Don't forget, this is a car without a roof. The plastic was just shattered. So without even the strength of the roof, there hasn't been that much effect. You can in fact open the door.
Would firefighters need the jaws of life to get access to somebody? No, you could actually open the door. That alone, that's a huge plus for first responders. How did they do that? Well, if you walk to the front, you'll see the engine crumple zone.
Bits fly out. But it's only really when you come around the front, you do see...
There's the crumple zone. The engine pancaked.
That massive impact. Around the other side, though, it still looks remarkably like a smart car. You can see the full shape of the door. Indeed, the door not only opens normally, it closes again. That does show how well that cage has worked on this impact.
Oh.
We were staggered at how well the smart seemed to have stood up to our high-speed collision.
So that's pretty good. Clever engineering. Impulse also involves toilet paper physics. You've seen those really, really big rolls of toilet paper, the large ones that they have in public washrooms. You may have noticed if you pull on the toilet paper slowly, the roll will roll. But if you yank on it quickly, the paper tears. How come? Well, you're trying to change the momentum of the toilet paper. If you yank quickly, small time, what do you need then to change the momentum of the toilet paper? A big force. The paper's going to rip. If you pull slowly, larger time, smaller force is required to change the momentum of the toilet paper. The toilet paper will start to unroll. You can do physics anywhere. There's something similar you can do with a wooden block between two strings. This is kind of a neat one. So it's really tough to see, but there's a tiny string right there. This red rope is just a safety line. But Mika, there's a string running from there to the top of the block, and there's also a string running from the bottom of the block to there. It's a little tough to see, but it is there. If you pull on that bottom string slowly, you can snap the top string. If you pull on the bottom string quickly, you'll snap the bottom string. You can actually pick which string you want to snap because of impulse. So we're going to do a really quick yank, snap the bottom string. The block had so much inertia, it hardly even moved. The string snapped. Pull slowly. Top string snap. Longer time, smaller force on the bottom string, constant force on the top string snapping. Okay. I want to talk about types of collisions. We're going to break collisions into two main types. The first type is where the objects bounce off of each other after the collision. Some good examples: curling, billiard balls playing pool, baseball and a baseball bat. Some car crashes, not all. There's a fancy physics word for that. Collisions where the objects bounce off of each other are called elastic collisions. And I'm going to start to use that word in the homework and in the lessons, so you'll need to know what it means when we're talking about collisions. Can you think of a good way to remember that elastic collisions bounce off of each other? I just think elastic like rubber ball. Elastic band is rubber, rubber ball bounces, is what my brain does. The second type of collision, Ella, is where the objects stick together after the collision. When a football player tackles and wraps their arm around the person they're tackling. Dart hitting a dartboard, assuming the dart doesn't fall down. Arrow going into a target. Bullet entering and sticking inside a target. Some car crashes. The fancy word is, well, it's not elastic, so we call that inelastic. So you have elastic and inelastic collisions. What I'm going to be doing is I'm going to be showing you several short little videos of two little carts on a little track in a physics lab, and they're going to be crashing. Sometimes the carts will collide elastically. Sometimes they will collide inelastically. Sometimes the carts will have the same mass. Sometimes it will be a heavy cart hitting a small cart. Sometimes it will be a small cart hitting a heavy cart. And our goal is to see, based on the physics that we've learned, we're going to see if we can predict which one is which collision is which. So here are my collisions, and I go view. Come on, computer. It's having to repopulate this. Taking a while. Details. Okay. Here's the first one. Watch. Fahim, watch.
Unequal mass exploded.
Okay. So there's an explosion. Here's the second one.
Equal masses. Explosion.
In one of those, the masses were identical. In one of those, the masses had one big one, and one lighter one. So here's the first one.
Unequal mass exploded.
Here's the second one.
Equal masses. Explosion.
Which one do you think had identical masses? Video 1 or video 2? Eric? Convince me. You know what? What was the initial momentum before the explosion as a number exactly? What must the final momentum be as a number exactly? Which means they must have same mass, same velocity. Okay? I agree. In the first one, which one do you think is the heavy mass? The one on the left or the one on the right?
Mass explosion.
Let's watch. Which was the heavier mass? The one on the left or the one on the right? Left. Okay? The next one, there's going to be 3 collisions.
Elastic, big mass, and small mass.
Here's the first collision. Was that an elastic or inelastic collision? Now, elastic collision. So what you're going to see are 3 consecutive elastic collisions. One is going to be identical mass hitting identical mass. One is going to be heavy mass hitting light mass. And one is going to be light mass hitting heavy mass. So let's watch this one again now that you know what to look for.
Elastic, big mass, and small mass.
First one.
Elastic, small mass, hits big mass.
There's the second one. Mika's rubbing his eyes. Got to pay attention, Mika.
Elastic.
Here's the third one. One of those, I think, stood out. Which one? First one, second one, or third one? Let's watch them again. Here's the first one.
Elastic, big mass, and small mass.
Here's the second one.
Elastic, small mass, hits big mass.
Here's the third one.
Elastic.
Which one looked different from the other one? I think the second one. What do you think the second one is? This one here. Come on, Mouse.
Elastic, small mass.
Is that heavy hitting light? Light hitting heavy? I think that's light hitting heavy. Yeah? It almost comes to a complete stop, and the other one barely moves off. What about an identical mass hitting an identical mass? In a perfect physics world, the identical mass, if it's an elastic collision, should come to a complete stop, and the second mass should take off at exactly the same speed as the first one. That would be 2 identical masses. So now we want to look at the first video and the third video to see which one is identical and which one is heavy hitting light. Here's the first one.
Elastic, big mass, and small mass.
I think that second mass left a little faster than that first. I think that second mass had less mass. Okay? And I think the third one is identical mass hitting identical mass. Oh yeah, it came to almost a complete stop. It passed almost all of its momentum on to the next one. Is that okay? Cool? Okay, now we're going to see 3 inelastic collisions. They're going to stick together. And it's going to be same mass hitting same mass, sticking together. Heavy mass hitting light mass, sticking together. Light mass hitting heavy mass, sticking together. Again, see if you can figure this out, Mika.
Elastic, big mass, hits small mass.
There's my baseline. Compare it to this one.
Inelastic, small mass, hits big mass.
That one gave me a hint, I think.
Inelastic.
That second one was a little strange.
Inelastic.
I think this one is either heavy hitting light or light hitting heavy. What do you think? Yeah.
Inelastic.
Why? Not much momentum because not much mass. And then when they stick together, now you have a big mass, so really small velocity because momentum is conserved. Okay, so either the first one was heavy hitting light or the third one was heavy hitting light. Let's see. Here's the first one.
Inelastic, big mass hits small mass.
And the third one.
Inelastic.
I think in the first one there was less of a slowdown. I think that was a heavy mass running into a lighter mass. I think in the third one they were identical masses. And you would actually get then half the speed afterwards because your mass doubled, so speed would be cut in half for momentum to be conserved. Back to notes. I like example 1, I like example 1, I like example 1. Example 1 is a nice question. A 1.5 times 10 to the 3 kilogram car traveling at 44 meters per second collides head-on with a 1 times 10 to the 3 kilogram car traveling 22 meters per second, in the opposite direction. If the cars stick together on impact, what is the velocity of the wreckage immediately after impact? Well, first of all, Scott, is there a collision? Sorry? This is a job for conservation of momentum. Scott, we want to be lazy but organized. Okay, so here's what Mr. Dewick suggests. Scott, how big is the first car? What's its mass? See it in the question? I'm going to be really lazy. Look up. What I do, I'm going to put a capital A above that. That's going to be car A. If you want to, you can write, let the first mass be car A. You don't have to, Sophie. I'll figure it out if you just label it in the question. I'm clever enough, and I think that's pretty clear. And I'm going to put a big B above the second mass. That's car B. Clear enough? Lazy but organized. A really important phrase I'd like you all to underline is that right there. Opposite direction. What does that mean? It means we're going to have to let one way be something and one way be something. We're going to have to let one way be positive and one way be, you know what? For lack of anything better, positive, negative. You could totally do it the other way around and we'll still end up with the same correct answer. Are we organized but lazy? I think we have accomplished our goal. We've labeled everything. We know what we're doing. What did you say? There was a collision? I usually tend to write the law of conservation of momentum. The sum of all the momentum to begin with equals the sum of all the momentum after. And now I'm going to analyze this collision. Scott, before the collision, what's moving? Car A, car B, both or neither? Were they stuck together before the collision or separate? So I'm going to go, momentum is what times what? So car A is going to be mass A, velocity A initial, plus mass B, velocity B initial, and then they collide. After the collision, Scott, what's moving? Car A, car B, both or neither? Can you read to me the sentence that starts with the word if? So stuck together, and then what is the? I think they're moving, because otherwise the answer would be 0, which, by the way, in a head-on collision could happen if the masses and velocities were identical. But I think stuck together, but moving. How do I write stuck together? In brackets, MA plus MB, V final. Scott, what am I trying to find? Which one? There's 3. Oh. I can probably do this in one line. How would I get the VF by itself? What's the bracket doing to the VF? So, I'm going to do this right here. I'm actually now just going to go. Usually I'd have to rewrite the equation one more time, but I'll take that. Let's go plug in the numbers. So VF is going to be M. 1.5 times 10 to the 3, that's 1,500, which is less writing and less typing, so I'm going to go with that. 44 plus m. 1 times 10 to the 3 is 1,000 times negative 22, all divided by 1,500 plus 1,000. I have no idea what the answer is, but this is a good one for all of you to practice typing into your calculator. I think we're going to need brackets around the top and brackets around the bottom. I think. Bracket 1,500 times 44 plus 1,000 times negative 22, close off the top, divided by bracket. Do you get 17.6? Positive or negative? So I guess here's what happened if I use these two tennis balls as my analog for the collision. Car A was coming in really fast. Car B was coming in not as fast. Wham, they collided, they stuck together, and they moved off forwards for Car A, backwards for Car B. Car B ended up changing its direction from negative 22 to positive 17.6. And I'll add the word forward. Although since it's positive and since they didn't mention north, south, east, or west, I'd be okay if you just wrote 17.6. I would assume you're telling me it's positive because you didn't put a negative in front of it, and I'm good with that. Oh, is this collision elastic or inelastic? Is this collision elastic or inelastic? Inelastic? So what you're seeing now with example 1 and example 2, I like example 2, I like example 2, this is a very good indication of what the written section of the momentum test is going to be like. And we're nearly done the unit. I'm thinking your momentum test, I could almost squeeze it in Friday. That would be awkward. Then we have a long weekend, so I'm not going to throw it at you on Tuesday after a long weekend. Probably Wednesday-ish. A curling stone that is traveling due east at mass A. It strikes a 12.5 mass B that is moving east at 1.2. I see east and I see east and I see east. Everything's positive. If I saw the word west, I would label any of the velocities with positives or negatives, depending on how it goes. What is the final velocity, magnitude, and direction of the second stone? So it looks like here we have one curling stone moving slowly, another one hits it from behind. Probably going to give it a bump so that it's going to move faster, I suspect. This is like getting rear-ended if you're in a car, for that matter. Is there a collision? Conservation of momentum. The sum of all the momentum you start with equals the sum of all the momentum you finish with. Mr. Dewick, do I have to write that every time? You don't. I will say, though, on the test, I'll give you a half mark if I just see that and you blank out on the rest. Like, you at least clued in it's conservation of momentum. That's worth something. Okay. Zaina, before the collision, what's moving? Mass A, mass B, both? I think both, and I think separate. So it's going to be mass A, velocity A initial, mass B, velocity B initial, and then they collide. The collision is the equal sign. After the collision, what's moving? A, B, both, or not? I think both. Stuck together or separate? I think separate because they gave me the velocity of the first and they want me to find the velocity of the second. So probably, okay. So we're going to have mass A velocity A final after the collision, mass B velocity B final. Zaina, what do they want me to find? That one there, I agree. What side is it on? The right? Left side's going to drop down like a domino. Then what? Good. And then what? Let's do that all in one step in our heads and feel a little bit of swag. Yes? Okay. So you're telling me the final velocity of B, it's going to be, you said the left side's just going to drop down. I agree. Well done. Then you said I would subtract MAVA final over, and then you said with a bit of a yawn, I would then divide by mass B. Yeah. That's got to be it. You've come a long way, all of you, in your ability to rewrite stuff. And hopefully I've convinced you it's a better place to get to. So much nicer. Alrighty, let's plug in numbers. In your homework, if you were feeling bold and you wanted to go straight to your calculator, in your homework, I would live with it. In our notes, we'll write it out. And on a test or a quiz, I would always write out the numbers. So if you make a silly mistake, I can still give you all the part marks. I've scrolled down, Zaina. What was mass A? Velocity of A initial? Mass B? Velocity of B initial? Minus 18. And velocity of A final? 0.65. All over. 12.5. I can make some predictions. I notice mass A lost momentum. It slowed down. That means mass B must have gained momentum. It sped up. So I can tell you the answer is going to be bigger than 1.2. If it's not, you've messed up. I have no idea what the answer is. What'd you get? 4.008? So 4.01 if I go to 3. Did it say specifically magnitude and direction in the instructions? So 4.01 meters per second. There's the magnitude. What's the direction? East. That's an at symbol there. That's a terrible at symbol. At east. Oh, was this collision elastic or inelastic? Did they stick together or bounce apart? Which ones bounce apart? Elastic band, rubber band bounce. Okay. I think, yeah, one more, we're done. The 550 gram, okay, first thing, grams. Nice try, Duick. I would cross out the 550. How many kilograms? How do I go from grams to kilograms? Aiden, you're right. And yes, and what's the answer? I saw you read your lips. So 0.55 kilograms. And you know what? That's going to be mass A. Oh, you know, hang on. Pick letters that are more clever. This is a can. Let's call it C for can. Easier to track. And then I see a 12-gram bullet. Nice try, Mr. Duick. 0.012 kilograms. And I'll call that mass B for bullet. Read the rest of the question. Do I need to let one way be positive and one way be negative? Or is everything nicely in the same direction? Do you see easts and wests? Okay, I'll call east positive because that makes sense to me. So I'll put a plus sign in front of the 25. I'll put a minus sign in front of the 250. And I'll put a minus sign in front of the 55. Those are all wests. This is definitely a collision, a bullet hitting a target. I guess they want me to find the Final velocity of the can. Okay. This is a job for conservation of momentum. Madison, before the collision, what's moving? The can, the bullet, both, or neither? Stuck together before or separate? So it's going to be mass of the can, velocity of the can initial. Mass of the bullet, velocity of the bullet initial. And then they collide. Afterwards, stuck together or separate? And both moving. Mass can, velocity can final, plus mass bullet, velocity bullet final. I hope right around now some of you are noticing this is actually pretty much identical to the question Zaina and I just did in terms of the setup. I think the only difference is there's going to be some positives and some negatives, but it's going to be the same procedure. Oh, what are we trying to find, Madison? Get that by itself. Left side drops down. Yes? And then what? Minus the MBVB final over. And then divide by MK. We can do that. We can do that. We can do that. The left side drops down. And then minus the mass BVB final. And divide by mass of the can. That's going to give me the final velocity of the can. What if they had stuck together? Oh, the masses would be in brackets, like the very first one we did. That's pretty much all I can throw at you. Head on, same direction, stuck together, or separate. I can't really make up much more than that. Let's plug in our numbers. What was the mass of the can, Madison? I've scrolled down. 0.55, and its velocity was 25 plus 0.012, and its velocity was negative 250, and then minus 0.012, and its velocity was still negative 55. All divided by 0.55. I'm not quite sure what's going to happen here. It's possible the can gets slowed down but is still traveling east. It's possible we could get a negative answer. That means the can actually got completely turned around and ended up going west after the collision. I don't know. What do you get? Sorry? Positive 20.7 or negative? Positive? Is it 20.7, folks, or not? I'm seeing some heads shaking. I say yes? 20.7? No, yes? Yeah? And positive? Okay, so it slowed down, but it still kept going in the positive direction. So, did it say magnitude and direction? So let's add the direction east. Yes? I wasn't sure because the bullet slowed down. Oh, but you know what? The bullet had so little mass that even though it slowed down a lot, that wasn't that big a momentum transfer because mass times momentum was not much compared to the mass of the can. Slowed it down but didn't turn it around. Okay, that makes sense to me. Elastic or inelastic? They didn't stick together. They went through each other, which isn't exactly bouncing off each other, but same dealio. Okay. What's your homework? Number 1? 2 is good. 3 is good. 4 is good. 5 is good. I'm going to skip 6. 7 is good. I'm going to skip 8. 9 is good. And 10. That's a lot. I think on Friday, which is the day after tomorrow, we'll press pause, and that will be a day for you to get all caught up. So in theory, you have no homework for the May long weekend. I don't like giving homework out over the long weekend. Maybe on Friday we'll watch a Mythbusters video and kind of go from there as well. Okay?